So in the previous episode, we noted that it's very, very nice to have specifically an orthonormal basis for your vector space. If you have specifically an orthonormal basis for your vector space, that gives you a very simple way to express vectors in that space as a linear combination of the basis. You can find the coefficients just by using the dot product, as opposed to earlier, we had to do row reduction to find those coefficients. So if you're working in a vector space and you have a basis that you're working with repeatedly over and over again, it can be a nice investment, a good investment to take that basis and replace it with one that is orthonormal. You can make that investment up front to make later calculations involving that basis a little bit easier. And to that end, let's talk about what's called the Gram-Schmidt process. The Gram-Schmidt process is an algorithm that's used to take a regular basis and turn it into an orthonormal basis. So let's go through that process. So the process starts where you have a set of vectors v1 through vk. These set of vectors are forming a regular basis for the vector space. You want to take these vectors and you want to manipulate them and transform them to turn them into an orthonormal basis instead. So step number one of that process is to take vector number one of your basis and rescale it and turn it into a unit vector. And this unit vector will be the first element in your new orthonormal basis. Let me demonstrate this first step in the context of this worked example. Here I have the vectors v1 equals 4 minus 1, 2, and v2 equals negative 1, 2, 0. And they span some vector space. What I would like to do is I would like to replace these two vectors with another set of vectors that form an orthonormal basis for this vector space. I'm going to construct the vector u1 by taking the vector v1 and dividing it by its length. I'm going to do this to turn the vector v1 into a unit vector. So let's go ahead and calculate what is the length of the vector v1. The length would be the square root of 4 squared plus negative 2 squared plus 2 squared. So that would be what? Root 21. And that would make the vector u1 equal to 4 over root 21, negative 1 over root 21, 2 over root 21. So this would be the first element in the orthonormal basis that I'm constructing for the span of these two vectors. Okay, step number two of the process. You need to create the second vector of your orthonormal basis. So you do that by taking the vector v2, the second vector in your regular ordinary basis. Take the vector v2 and subtract the projection of v2 onto u1. What's essentially happening here is we're taking the vector v2 and removing the portion parallel to u1. We remember from our lesson on vector dot product and vector projection that when you project one vector onto another, what is represented by that is the portion of v that is parallel to the vector you're projecting onto. And then if you take that vector and you remove, subtract, delete that projection, what is left as a result of that process is the portion of V that's perpendicular to W. So this is the idea that we're using in the Gram-Schmidt algorithm. We're going to force the vectors in our basis to be perpendicular by calculating the projection and then removing or deleting the projection from our basis vector so that what is left behind is perpendicular to u1. So in the context of our example, if I want to find the projection of v2 onto the vector u1, then I could do that, for example, by dotting the two vectors together, v2 dotted with u1 over u1 dotted with u1 applied to the vector u1. Now u1 is a unit vector, so u1 dotted with itself is for sure going to return a value of just 1. So then let's ask ourselves what happens when we dot together the vectors v2 and u1. So looking at that expression, v2 dot u1 would be equal to negative 4 over 21 and negative 2 over 21. So in total, negative 6 over 21. And that scalar would then be applied to the u1 vector. So copying the u1 vector from earlier, that would be 4 over root 21 minus 1 over root 21 and 2 over root 21. If I follow through on that scalar multiple, what I get is the vector 24 over 21 with no root, negative 6 over 21, and then minus 12 over 21. So this is the projection of v2 onto the vector u1. This is the portion of v2 that is parallel to and aligned with u1. Now let's take the vector v2 and delete, subtract, remove the portion that is parallel to u1. Let's go ahead and take v2 and subtract the projection that we just found. We're subtracting the projection that we just found, negative 24 over 21, 6 over 21, minus 12 over 21. And so if we complete that vector subtraction, then we get, I think, in the first entry, 3 over 21, 36 over 21. And then 0 take away negative 12 over 21 would be positive 12 over 21. So what's left at this moment is a vector that is perpendicular to u1, the portion of v2 that was perpendicular to u1. So this guy points in the right direction. However, unfortunately, this guy does not seem to have the correct length. To be an element of an orthonormal basis, we need to change this guy so that it has a length of 1. So that's the next step of the algorithm. Now that we have taken v2 and subtracted its projection onto u1, we need to take the result and rescale it so it becomes a unit vector. Take the result and rescale it so it has a length of 1 unit. I'm going to start by rescaling this vector just to simplify it to make calculating the length easier. I'll take this vector, for example, and multiply it by 21 over 3. And for example, that action will turn my vector into 1 in the top position, 12 in the center position, and 4 in the final position. And then I'm going to go ahead and turn this vector into length 1 by dividing out whatever length it has right now. So the square root of 1 squared plus 12 squared plus 4 squared would be the square root of 1 plus 144 plus 16. So that's the square root of 161, if I've got that right. So finally, here's my u2 vector. My u2 vector would be 1 over square root of 161, 12 over square root of 161, and 4 over square root of 161. That would be my second vector of my orthonormal basis. So that would conclude this process. I have replaced this basis with this orthonormal basis, u1 and u2. I would much prefer to work with these two vectors because it's going to make it easier to find linear combinations and spans involving this orthonormal basis in later calculations. We can go ahead and look at this situation on GeoGebra. Here in GeoGebra, this blue slanted plane is the vector space formed by the span of V1 and V2. And what you can see in black here, these two black vectors are the original basis vectors V1 and V2 for this vector space. And we can see that the vectors v1 and v2 are not perpendicular. They do not sit at a right angle. The angle between them seems to be larger than 90 degrees. We can also see that the vectors v1 and v2 are quite long. The vector v1 being all the way up here, and the vector v2 being maybe at least 2 or 3 units long. So what we have done is we've replaced this black basis of the vectors v1 and v2 with the orthonormal basis consisting of these two purple vectors given here. This purple vector here is the vector u1 that we obtained by just taking v1 and rescaling it. So this purple vector here is the u1 that we calculated by rescaling v1. And then this purple vector off here to the side is the vector u2 that we calculated. This vector u2 that we found by taking v2, deleting the portion that was parallel to u1, and then rescaling the result so that it had a length of 1 unit. So now you can see the purple basis that we have found is orthonormal. Both of the vectors have a length of 1 unit, and we can see that the vectors are sitting perpendicular to one another. So we've taken this old basis and we replaced it with this nice orthonormal basis instead. Now that's an example of the process when your basis only has two vectors in it, but you can imagine how the process extends if your basis had 3 vectors in it, or 4 vectors in it, or 5 vectors in it that needed to be transformed into an orthonormal basis. So for example, if you had a third vector that you needed to work on, what you would do is you would take your vector v3, you would project v3 onto u1, you would project v3 onto u2, and then you would take v3 and subtract those two projections. Subtract those projections to delete the portions of v3 that are parallel to these two other vectors. And that's going to leave you with something that's then perpendicular to these two other vectors. Then take the result and rescale it to make it into a unit vector, and then this unit vector would form your u3 for the basis. So that concludes today's video. Today we talked about a process for taking a basis for a vector space and transforming it into an orthonormal basis, typically as an investment to make the basis easier to work with in subsequent calculations. To turn a basis into an orthonormal basis, start by taking the first vector in your basis and rescaling it and making it have a length of 1. Then take the second vector out of your original basis and project it onto u1, and subtract that projection from your v2 vector. The result of that is going to be perpendicular to u1. So then just rescale that result and make it into a unit vector, and that's going to form the second element of your orthonormal basis. So that's how this process evolves.